use their slides. I'm just gonna give you an overview of the state of quantum money today, roughly what I believe the opportunities are in this space, what I believe we are experiencing as the start of the next age of the centralized money, the centralized financial instruments more generally. So this is, it's going to be less quantum and more about the opportunities that quantum affords in Web3 and decentralization. So hopefully a slightly lighter talk than the one that I gave yesterday on contextual cryptography, which was a bit technical. So first things first, what is quantum money? What do we mean when we say quantum money? Quantum money has a lot of different versions. All of them are based in some form on the idea that quantum states cannot be copied. So one of the big differences between quantum objects, quantum particles, so think photons, quanta of light, think atoms. You can encode quantum information into many different kinds of matter and energy. But one of the distinguishing features is that the state that this matter can be in cannot in general be copied. The process of transforming it and observing it, so trying to understand the state of your system, the state of a photon that's flying in a fiber optic or in a laser, the state of an atom that's suspended in some magnetic field, intrinsically has a chance of destroying the information that's contained inside. If you don't already know how the information is encoded, there is no physical way to do a measurement or an extraction without incurring the cost of erasing the information. And this is a very powerful principle. It's inescapable. There is no avoiding it. It's a mathematical fact. It's not an experimental reality. It's a mathematical reality. And it's been used over time to do many different things with quantum systems. But one of the most interesting to us is that this kind of unclonability can be used to store value. Because ultimately, one of the things that in practical life needs to be hard to clone is anything that we use to store value. Anything which can be exchanged for other goods, any universal equivalent that we have, such as cash, but also precious metals, gold, should be hard to copy. That's in fact the definition. That's why we use it to store value, because you receive it and you have a certain amount of cash, and that determines what you can do. If you could print more cash, then cash would be worthless. Maybe it would be worth it for other people, but as long as anybody can print cash, then cash loses its meaning. Same for precious metals. They're rare, so their supply is finite and fairly easy to control, and you can use them to store value this way. So quantum systems present an interesting opportunity. Because of these principles, you could use physics to create something which holds value. The system itself can be used to encode information, and anybody who wants to spend the, let's say, €1 that's stored in this photon has to necessarily perform a procedure that destroys the photon. They no longer have the right to spend that euro, they have spent it, and now it's gone somewhere else. And this is very similar to what happens in blockchains. So the new era, well, at this point, the current era of decentralized money, the era that we live in with layer ones, with Bitcoin, with Ethereum, with all sorts of coins, is all based on the same principle. You want to have some way of ensuring that this value cannot be transferred twice. You have the right to spend 1 Bitcoin or a few Satoshis. 1 Bitcoin is now very expensive. And yeah, once upon a time, buying 1 Bitcoin was a good idea. Now it's not cheap. But you have some system which enforces that this spending can only be done once. And the way we came up with originally was with banknotes. Now, in this era of internet money, with a ledger, some kind of system that makes it convenient for everybody to just stick with this rule. So you have some form of record of who got how much and then transferred how much to someone else. And this record is kept consistent by enforcing a penalty for anybody who deviates. So you have to spend a lot of money to mint a block, or you have to put a lot of money at stake to mint a block. And if you deviate, the cost to you is that you will lose that money, either because you've now burnt the electricity and you don't get the payout in Bitcoin, or because the payout that was on the block is no longer there in Ethereum and you get slashed because you participated in the wrong election in the wrong side of the chain. And that is a very interesting solution. It's a very clever solution, but it has one big disadvantage compared to ordinary cash, which is that it is not a peer-to-peer process anymore. It is peer-to-peer in the sense that I can send anybody money, but there is a general centralized record that needs to be kept to ensure that the spending is not done twice. There is a big overhead on it, either because we need to waste computational power for proof of work, or because a lot of people have to have a lot of money frozen at stake for proof of stake. With cash, as long as you imagine that counterfeiting is hard, you don't need any of this. You go around with money in your pocket and you pay for a coffee. Nobody really needs to know. Of course, the person who sells you the coffee probably has to keep their own records and declare this income for tax purposes, but the process of exchange itself is not recorded anywhere, which makes it massively localized and massively parallel. We spend money constantly, we spend cash constantly at scale with no infrastructure needed other than us walking around and carrying some lightweight pieces of paper, which have been designed to be hard to copy. That's the idea. And nobody really even has to verify the serial numbers on these pieces of paper. We just trust that with good probability, it is hard to make counterfeits. If you go to a shop, they're not necessarily going to look at your bill, look at the serial number and think in their head, okay, the serial number looks legit. They have no real way of knowing. So the trust in the unclonability of cash is what makes cash what it is. It's an instrument that you just carry around, locally exchange, and there is some process which gives you confidence that the value you received will not be challenged. Nobody has to know. It's just done there. So here is where the opportunity comes with quantum money compared to the current era of the centralized cash, the centralized money. Right now, we have a system that is expensive to run or otherwise requires a certain amount of financial stake to run properly. And more than that, is centralized. We have achieved protection against double spending. This is no longer necessarily tied to a central authority per se, or at least not one of the central authorities that we used to have, like central banks. So we did achieve part of the original idea of self-sovereignty in money handling. Our exchange of value is in our own hands. We manage the system, but only in the part that we decoupled it from central bank authority. We only decoupled it from somebody deciding how to devalue money or hypervalue money. But we didn't really decouple it from some centralized system or a bunch of people that hold a lot of stake or a consortium of miners that has the authority to decide who transacts what. So that part of the idea is still in limbo. And here is where the next generation should come, the next generation of technologies should come and fill the gap and complete that vision. Cash should be something which is electronic, yes, probably not a piece of paper that we need to carry. That is also part of the sovereignty of this. It's hard to make a banknote. You cannot really make a banknote easily. Somebody has to have the instruments to manufacture it correctly. And you shouldn't be able to manufacture it yourself for obvious reasons. But the digital value is what we want to achieve in a way which is similar to cash, but has this property that we cannot easily double spend it. And quantum states kind of do this. That is one of the fundamental properties of quantum systems. If you can carry around the quantum state for long enough, and you can use it to encode some information in a way which cannot be copied, then that information can be used to redeem the euro, the digital euro, let's say. And in the transfer, that state gets destroyed and the information is transferred into another state. From an atom in my wallet to an atom in someone else's wallet, it's obviously more complicated than this. It's bigger systems, but to simplify, a photon in my wallet, a photon in someone else's wallet, and the value has been transferred. This is digital. It's something that, it's not digital in the classical sense. It's not bits on a fiber, which are just electrical signals clearly up or down. It's digital in the quantum sense. It's photons that encode in their state some quantum information, but it has the same properties. It still travels over fiber optic like our current internet. More expensive fiber optics, which are put in place by people who are slightly more skilled. But nonetheless, the similar infrastructure, and it can be exchanged in a peer-to-peer way. And so the next opportunity in digital money, and what some of us are working towards quite hardly, is to achieve this idea. It's cash that you have that is digital, so it can be transferred over long distances with a suitable fiber optic network, let's say. That's one of the properties that we want to have. So digital cash, it should be safe against double spending, otherwise it's not suitable for cash. Check, that's what unclonability of quantum state affords us. And it should be something which doesn't require a centralized authority or a centralized power stake. It should be truly peer-to-peer. It should be truly self-sovereign. I have my money, I spend it locally, wherever I am, nobody needs to know. Not because I have anything to hide, but because the system becomes decoupled from connectivity issues. It becomes decoupled from power issues, from political issues. Nobody has to decide that my transaction should be included in the chain. I just went to Mark with my wallet to his wallet, and I transferred the value for €1. I'm not sure what I'm buying from Mark for €1, but coffee, let's say, or something. And that nobody should be able to censor that. Nobody should be able to say, oh no, I don't like that transfer, or no, you didn't pay enough fee to me for me to include that transfer in this block. You'll have to wait. None of these should be part of the properties of cash, and with quantum cash, you could do this. Now, there are some challenges. It is an idea, it's a very old idea. It's been there for more than 30 years in some form. There's been many, many iterations proposed for how to use quantum systems to implement some kind of store of value. And many of these ideas have significant shortcomings. There are challenges, or there were flaws in the implementation because we didn't fully understand how certain aspects of quantum information worked, which we now understand much better. Also, the way that cryptography was done in the, let's say, 80s or 90s is very different from the way that cryptographers work today. It's a lot more sophisticated. The tools are evolved. But we now know of a few different options for how to implement this kind of financial instruments using quantum systems. There is some research that still needs to be done theoretically, but some of the schemes are already potentially prototyped today. There are some technical challenges, and these are significant. And this is where things need to move forward for this vision to actually get implemented. One of them is that we need to be able to store these quantum states. If we want the unclonability to be purely, if we want the fact that you cannot double spend to be purely based on the fact that there is a quantum system that holds a quantum state that cannot be copied and not some other intermediate solution, then this quantum system has to live long enough for me to spend my banknote. And that is not a few milliseconds. I get paid, I take my cash, I am not gonna run like 3 seconds, I have to spend all of it in some shop. It's gonna have to stay in my wallet for days, weeks, months, possibly years. Which means we need some kind of quantum memory. We need some way to store quantum states, either hopefully in our pockets locally, but at least somewhere for a long period of time. And unfortunately, that doesn't yet exist, which is a bit sad. We do have quantum memory. We have ways of keeping quantum states hanging around for a little bit. That little bit is milliseconds. For some of the recent advancements, maybe a few seconds, but that's a stretch, and there's a good probability that the quantum state will get broken in the process, which is not great for money. You don't want your banknotes to have a maybe 30% chance of fraying away when you store them for a few seconds. That's not great. It doesn't work. But this is steadily improving. And one of the interesting side effects of quantum computing research, quantum computing is a completely different field from quantum cryptography. The kind of technology that's used is different. It's much more complicated. It's much harder to perfect. And it already received a significant amount of investment. But one of the pleasant side effects of this research is that we will shortly have useless quantum computers, which is not great for the companies that manufacture them, but it is great for people who want to store quantum states. Because the first step in building a useless quantum computer before you build a useful one is that your quantum computer has to, at the very least, keep some state stable for long periods of time, more than seconds, hours, days, indefinitely in reality. And so we will at some point get news from Google, IBM, Quantinuum, any of the big companies, Xanadu, PsiQuantum. I'm just trying to be fair to Quera, just trying to be fair to the various technologies that are available around. We will get news that somebody finally achieved one logical qubit. And one side of the world will be extremely excited because, yay, I mean, big reveal from Google, they have one logical qubit. They're gonna make some nice press release. They're gonna say that there's parallel universes. That's all great. And the other side of the world, so people who actually work in quantum computing will probably start pointing out that, yeah, great, but you can't do anything with it. You can't do operations with it. You have 10 logical qubits, but you can't really perform anything interesting on them. But for people who need quantum memory, that is incredible news, because that means you have 1 qubit of memory, and then 2 qubits, and then 5 qubits, and then 10 qubits. And we can use that to store states for a longer period of time. But that's like storing money in a vault. You have to send it to someone who has a quantum computer. They will keep it for you, and then you have to connect to them again to get it and spend it. It's an intermediate solution, but it's not the final thing. The final thing would have to be miniaturized and portable. So we need, at the end, we'll need some kind of quantum money that we can store in the equivalent of a digital wallet and that we can carry around. And that will take a bit longer. But it's something that requires technological investment, technological advancement. And the only way to get that investment and that advancement is to start providing interesting applications for it. And financial applications don't need to be long-term in the beginning, which is one of the interesting aspects of quantum money that are not usually discussed. Not everybody who exchanges value has to carry it in their pockets for days or weeks or months. A lot of interesting exchanges of value are peer-to-peer between, let's say, financial institutions or on financial markets. And these are millisecond time, maybe short second or 2-second times. These are very fast. They still require peer-to-peer. They still require some kind of sovereignty if you want full access to a market, but you don't necessarily need to hold these states for very long. And so if we start developing quantum money applications that span different time scales, going from sort of fast settlement applications and then moving towards like short-term applications and then longer-term applications, we can push the next stage of digital internet money forward in terms of technology. And now we want to exchange this with somebody. Great. How do we do that? We can do it over fiber optics, but not really the fiber optics that make up our internet, because it's not just one cable. It's one cable with a repeater after a while, and then another cable, and then another repeater, and then another cable, which is great for classical signals because you can just absorb them and re-emit them. But it's not great for quantum signals, because the moment that you absorb one, you observe it, that's it, it's done. You have, like, somebody has burnt your money on the way, which is, again, not good. And so we need to have deployment of quantum internet infrastructure, as it is often called. And this is, it's different from the current infrastructure, but not that different. It is mostly fiber optic and satellites. So fiber optic for the short-term, for the short-range networks, clusters of nearby entities, and laser sort of satellite transmission over longer distances to preserve the coherence of the quantum states, to avoid this destruction of the money that we want to transfer. And this is also something which requires a significant amount of advancements, technical, from people who know how to do this, and a significant amount of investment. And you only get investment in this if you can start providing applications that people want to pay for. Luckily, we have some test nets already, because some of the financial institutions in clusters around the world have decided that, yeah, okay, it's worth paying for some fiber optic to be laid down, and then we figure out what to do with it. We have some test applications, key distribution, and we'll probably get more, maybe. But in order for this to be longer range and larger scale, for this to be actually to allow you to spend money on things, it needs to be connected across the world. And providing new applications, new cryptographic applications that run on them, new financial applications, which are the ones people care about, is a great way to push this next stage of decentralized money forward. So it's an infrastructure challenge, it's a technological challenge, but it is one which at the end has a true digital, quantum digital equivalent of the cash that we have today. We will have really replaced cash with something that has the same properties. Somebody mints it, and that's it. It goes around, and the fact that it cannot be easily counterfeit, it cannot be easily copied, is what gives it value. Nobody needs to establish it by other means. Nobody can control it by other means. And that's the vision of quantum money in the world of decentralized money, why we want this to be the next stage of sort of peer-to-peer financial instruments. Thank you for listening to me.
Thank you very much. Thank you very much for stepping in and talking about quantum money. Really appreciate it.